All right, in this video, I want to find the point of intersections of these two exponential functions over here, and then I want to sketch the graph out as well. And I want to find the slope of the tangents of these two equations at the intersection points as well. So the first thing I'm going to do is I'm going to find the intersection point by making the first equation equal to the second equation. Now I want to solve for x. So I'll move the e to the 1 minus x to this side, and I'll move the plus 1 to this side. So I have e to the x minus 1 plus e to the 1 minus x equals 3 minus 1 is just 2. So now to solve this, there's a couple of different ways I can solve it. I can basically split my exponents. So by using rules of exponents, I know this is the same as e to the x divided by e to the 1. And I can just write that as an e. I don't need the 1 there. And this is the same as e to the 1 divided by e to the x. This equals to 2. So now I'll make a common denominator over here. So I'm going to multiply the top and bottom here by e to the x. And over here, I'm going to multiply the top and bottom by e to the 1. That way I'll have a common denominator. So e to the x times e to the x is just e to the 2x. We just add exponents. E to the 1 times e to the 1 is just e to the 2. And I have a common denominator of e to the 1 times e to the x. And this all equals to 2. Next, I'll cross multiply my denominator over to the other side. So I have e to the 2x plus e to the 2 equals 2e. I won't write the 1 anymore. And then I have e to the x. And now this is a bit difficult to solve, but if you notice, this is a quadratic exponential equation. This is basically my middle term over here, which I'm going to move to this side. So I have e to the 2x minus 2e e to the x plus e to the 2 equals to 0. This is a bit easier to tell now that this is a quadratic trig equation. Now, if you can't factor this instantly, you can just go let a equal to e to the x. So then this is going to turn into a square minus 2e a plus e square. This equals to 0. So this should be a bit easier to factor. This is just a perfect square over here. You could have done it straight in that step if you recognized it. I just did the substitution to make things a bit easier. If I perfect square this, it's just a minus e whole squared equals to 0. Now I can replace the a back with e to the x. So e to the x minus e squared equals to 0. And then I can just solve this. So it's just e to the x minus e equals to 0. I don't need the square because if I square it on the other side, the 0 just stays as 0. Then I can just move the e to the other side. And now the bases are the same, so I can cancel them. I'm just left with the exponents. Remember, there's a 1 here. So x equals to 1 is the x value of our point of intersection. To find the y value, I can sub back into either of the two equations. Now, in this case, we only have one point of intersection here. That's what the perfect square did. But remember, for an exponential function, you can have no points of intersection. You can have one point of intersection like we do in our case over here. You can have, that's not the best exponential function, but you can have 2 points of intersection like this case. Or you can also have infinite points of intersection if they're just on top of each other. Those are the 4 cases for exponential functions. In this case, we just have one point of intersection with the x value of 1. I can find the y value of this by subbing it into either equation. I'll just sub in this one because it's a bit easier. So y equals e to the 1 minus 1 plus 1, which is just e to the 0 plus 1, which is just 1 plus 1, which is 2. So my point of intersection for this function is 1, comma 2. Now that I found my point of intersection, I can sketch these functions out over here. If I look at this first function over here, I have my horizontal asymptote at y equals to 1. And I know that this is exponential growth, e is exponential growth, and my vertex, or my y-intercept, which is normally going to be at 2, 1 above this, is moved 1 unit to the right, and it's moved 1 unit up. So my y-intercept, which would normally be at 2, 0, in this case, is going to be at 3, comma 2. And for this function over here, I have to rearrange this equation in order to sketch it out. Oh, also 1, 0 moves 1 to the right and 1 up. So the point of intersection is actually 1, comma 2, not 3, comma 2. That was a tiny mistake, because it's normally at 0, 1. I move 1 to the right, 1 up. And then this is exponential growth here. The first function looks like this, where this point is 1, comma 2. And then for this function here, I actually have to rearrange this to sketch it out. So y equals negative e to the negative x plus 1 plus 3. I've just put in a bit better form, transformation form, so it's easier to sketch. And now I have to factor out the k value, because you can't have a k value and a d value and leave it unfactored. So now I can sketch this equation using my transformations. My horizontal asymptote is at y equals to 3. I have a reflection in the x-axis and a reflection in the y-axis as well for this one. So a regular graph looks like this, exponential growth. If I reflect it in the x-axis, it looks like this. Now, if I reflect it also in the y-axis, it looks like this. So this is going to be the shape of my function for the second one. I know that the y-intercept would normally be at 0, 1. The reflection in the x-axis is going to move it to 0, negative 1. Reflection in the y-axis is not going to change anything. Then it's going to move 1 unit to the right. So now it's at 1 and negative 1. And then it's going to move 3 units up, which places it at 1 and 2, which is basically the point of intersection as well. So this second function here is just coming like this. It just touches at one point over here, and then it goes like that. You could always find the x and y intercepts as well if you wanted to make the sketch more accurate, but it's not needed in this case. This is an accurate sketch of the function where they both have one intersection point at 1, comma 2. And the last thing we need to do is we need to find the slope of these two functions at this point. So for the first function, if I derive this, the derivation of this is just y prime equals e to the x minus 1, and then times the derivation of the exponent, which is just 1. So y prime is just e to the x minus 1. The x value at the point of intersection is 1, so I'm going to sub in that to find my slope. So I have e to the 1 minus 1, which is e to the 0, which is just a slope of 1. So the tangent line for the first function has a slope of 1 over there. Let's calculate the tangent line for the second function. If I derive this function here, the derivation is y prime equals negative e to the 1 minus x. And by chain rule, I'm going to derive the exponent, which is negative 1. So this is just going to be negative times negative is positive, e to the 1 minus x. And I can sub in my x value of 1. So my slope is e to the 1 minus 1, which is e to the 0, which is also positive 1. So these two functions have the exact same tangent line as well. In this case, they both have a slope of 1. You could find the tangent line if you wanted as well, but it's not required in this question.